So to title these notes, we are continuing from yesterday, but the title of these is going to be Indefinite Integral. So, what symbol is usually involved with integrals? The little S thing. What does the S stand for?
Sigma.
Not sigma, sum. This is saying the sum. It means, it's still, the sigma also means to find the sum of something, but this is literally an S that stands for sum. Now, typically, what do we do with this integral symbol? What do we put on it?
The lower and upper bound.
Yeah, a lower and upper bound. When we put an A and a B, it's called a definite integral, meaning the integral is defined. When we say indefinite integral, we are saying the integral is not defined, so we are not going to put an A and a B. We're just going to say the integral of f of x dx. So no upper bound, no lower bound. Just write it like that. All right. So the answer to this, when you take the integral of this, you end up getting capital F of x plus c. Now, in the notes last night, what did we talk about? This is the antiderivative. Does that make sense? So, when we talk about what we've been doing the past couple days, when you have a definite integral and you have the boundaries, you're saying what is the area underneath the curve on that specific interval. If I take away the interval, I'm saying what's the area underneath the curve and can I have a formula to find it? This is the formula that allows you to find the area underneath the curve anywhere you want to look. So if we relate this back to derivatives, remember we had two situations with the derivative. We said, oh, the derivative represents a slope. So if I plug in a specific point, I'm going to find a specific slope at that instant. Or if I take just a general derivative, then I get an equation and I can plug in any number I want and get any of the slopes anywhere. We're doing the same thing. We're just doing the backwards version of it. So a definite integral says what's the area for a specific interval. An indefinite integral says now I'm going to find an equation so that I could find the area anywhere I wanted. Does that make sense, the difference? Okay, so you did this last night, you just did it with different notation. This, when you integrate something, you find the antiderivative. That's what you're finding when you integrate, okay? So we have just found a new inverse operation, right? Inverse operations are like add and subtract, multiply and divide, log something, exponentiate something, that means put it as like it is a base with an exponent. A new inverse operation that we have now is derivatives and integrals, or derivatives and antiderivatives. They undo each other. Okay, so we've learned something new. This is the opposite of what we've been doing the entire class so far. Okay, so what this means, I'm going to say that this notation right here is asking for the antiderivative equation, aka an area under the curve for any interval on the original function.
So if it had like a lower and upper bound, it wouldn't be an antiderivative?
It'd be kind of like, they wouldn't call it an antiderivative. Sorry, that was too zoomed in. They wouldn't call it an antiderivative, they would just say find the area under the curve. But that essentially, yes, it would be like the antiderivative at a specific instance.
And this is just like wherever we want it.
Yeah.
Okay.
Yeah, it's kind of like when you find the derivative at a specific point, you don't call it the derivative at a specific point, you call it the slope.
Right.
You know, like you call it a different name. So when we find the area underneath the curve at a specific interval, we just say that's the area.
Right.
We don't say that's the antiderivative evaluated at something. We just say, oh, that's the area. Yeah. All right. So that notation is asking for the antiderivative equation, which is the area under the curve for any interval. So once you have this equation, and it's not just one equation, right? It's plus c, so it's plus any constant. It could be plus 0, plus 5, plus whatever. So instead of saying this represents one equation, we could say it represents a family of equations, but the area underneath the curve you could calculate if they gave you enough information to find c. And you could say, I want the interval from 1 to 10, and you could do that with that equation. Or you could say, I want the interval from -1 to 2. You could do that. So you could, any interval you wanted, you could then work with, okay? All right, how are you feeling about that? So when you see the problems today, they're not going to write them like the notes from last night where it just said f prime of x is this, tell me what f of x is. Or lowercase f of x is this, tell me what uppercase f of x is. Although some problems will be written that way. Today when they write the problem, they're going to say, we'll do a couple examples so we can feel comfortable with it. They're going to say integrate, find the indefinite integral of x to the third plus 5 sine x dx. And in your head, you're going to say, okay, I need to use my antiderivative rules. All right.
So we use this when there's no upper and lower bound.
Mm-hmm. Mm-hmm. All right, so what's the rule if you just have a term that has an exponent? What do you do with the exponent? You add 1 to it and divide by that number. So this is x to the 4th divided by 4. Okay. How about sine x?
Becomes
Negative cos x, okay? And the 5 just stays in the front. So like when we took derivatives, how if we had a coefficient that stayed in the front? Same thing here. If you take the antiderivative, that coefficient's just going to stay in the front. Yeah?
So my question is what if you, how would you know if something was the result of the product rule, and what would you do to find the antiderivative?
So once we do integrals for a while, we're going to get to the point where we're going to say, okay, now we've done all the simple ones. Now we have to start looking at things where like you really can't simplify them at all. You just have to know how more complicated procedures. And we will deal with problems like that. It's called substitution. That's the process that we'll use. For now, every problem that you're ever given that appears to be a product rule or appears to be a quotient rule can be simplified somehow so that it's not. So everything that we're starting off with is fairly simple. Once we get comfortable, then we'll move on to the more difficult stuff. Yeah. So we're going to say this one, like we said, we bring the coefficient, and it was negative cos. So that'd be negative 5 cos x. And then we always have to add a plus c on the end. And we actually, if you look in the back, there's some more baby animals that can die. So can somebody look and tell me which one is the one where you didn't add plus c?
Baby hedgehog.
Okay, baby hedgehogs die if you don't put plus c. And then with integrals, if you don't put the dx, what is it that dies if squirrel? Baby squirrels die if you don't put the dx. So we have more baby animals that are at risk now that we have learned more about integrals. All right? I don't think so. So now we're going to start watching out for baby squirrels and baby hedgehogs. Okay? All right, so we have this. You can leave it written like that if you want. I like to take the divide by 4 part, and I like to write that as a coefficient. So when I do my answers, I typically say 1/4 x to the 4th minus 5 cos x plus c. But if you want to leave it as x to the 4th over 4, that is totally fine.
Would you put capital F of x equals?
You could, typically when they write the notation like this, then you just say your answer like this. If they say f prime of x equals, then you would say f of x equals. If they say lowercase f of x equals, then you would say uppercase f of x equals. So the answer notation is usually dependent on the original problem notation. And with this particular notation, you typically just say this.
Okay.
And that's because this original problem did not have an f of x equals something. Good question. All right, let's do another problem. So for this one, we're going to do the integral of 4 square root t minus secant t tan t times dt. Does anyone know why I'm putting this part in parentheses? Yeah, that's your function. And remember, all these integrals are representing areas underneath curves. And the most basic way we ever found that was to use rectangles. So this represents the height of the rectangle, because remember we plug an x value in and we find the y coordinate, and that's the height. And this represents the width of the rectangle. So we always have to group all of this together because it represents the height. Okay, that's why I'm putting parentheses. All right. Now, when you write the integrals, if you feel comfortable looking at something that's a string of a bunch of different pieces and working with it as a group, you can do that. If you don't feel comfortable with that, you can use your properties of integrals, which means we like break it apart into little pieces, which sometimes when you're dealing with something big or something complicated will like calm your brain down and make it feel a little bit easier. So if you wanted, we're going to go ahead and rewrite this one, and we'll try it this way, and if you guys don't like it, we can go back to doing the whole thing all at once. So what I'm going to do is I'm going to take the 4, the coefficient of 4, and pull it out to the front, because one of our properties said that we can take coefficients and move them to the front and just let them kind of hang out. And then just like normal, I am going to rewrite the square root of t. And how should I rewrite it? T to the 1/2. Okay, and now that I've split it apart, I'm going to make this the second piece. I'm going to put a dt right there. And I'm going to say minus, and then I'll do the integral of secant t tan t dt. So I took the two different terms and I split them apart into two different integrals. Notice I did not try to split this one because there's no such thing as a property of integrals that allows you to split multiplication. You can split things that have been added and subtracted, but you can't split multiplication. Okay? All right, so I'm going to ignore the 4. I have an exponent of 1/2. What do I do to my exponent? Add 1. So 1/2 plus 1 is 3/2, and so I'm going to be dividing by 3/2. So I have t to the 3/2 divided by 3/2, and I've got a 4 in the front. So what do you do with that 3/2? Yeah, we multiply by the reciprocal, or we keep the top and flip the bottom and multiply them, right? So that means we're multiplying this by 2/3. So that would be 8 over 3. So it would be 8/3 t to the 3/2. Okay, so we simplified that first piece, and then we're going to say minus. We have to think about what would have given us a derivative of secant tan, and that was secant. What's your question?
The c doesn't have to come in yet?
Not yet.
Okay.
We put the c at the very end. So the antiderivative of secant tan would just be secant. And that's because when we first learned about derivatives way back when, we said, oh, the derivative of secant is secant tan. And so now when we're going backwards, it's going to be the backwards version. So we're going to say minus secant t, and now we can put the plus c because we're doing the whole group at once. All right? So minus secant t plus c. Yeah.
Where did the sum go? Is that just like
The s?
Yeah.
The s is saying that whatever you find, you're going to find the area underneath the curve. So if you do evaluate it, you are going to get a sum. That's what the s means. And here we're saying this is not a function. We're saying this is an antiderivative, and if you do plug in numbers, you are going to get a number. But right now we're doing like a general answer, and so we just get an equation as an answer, and that's it. Yeah.
So, for the secant tan, did we look at the chart that we made last night?
Yeah.
To do it?
Yeah. So this would have been something, basically this is one of the trig derivative antiderivatives that you memorize. And some people I've noticed, they prefer to have two sets of things that they've memorized. In the beginning of the year, they memorize the derivatives. In the middle of the year, now that we're at the middle of the semester, now they memorize the antiderivatives, and in their head they have two separate things they memorized. I have a tendency to think, based on what I memorized at the beginning, what's the backwards version of that? That's how I think of it in my head. Whichever way you think of it is fine. It's just the way that you remember. So in my head, I'm thinking, this is the answer. What did I take the derivative of to get there? And that was secant. Okay. All right. Let's do one more. I want to do this one because I think that the variable would mess me up if I was a student. So this one is going to be the integral of 6 theta squared minus 7 secant squared theta d theta. So I know as soon as we see those thetas, we're less comfortable, right? Because it immediately reminds us of like angles and trig, and we tend to not like trig. So, but if you think about it, it really is just in the place of an x. It works the exact same way an x would. It works the exact same way a t would. So if we look at this, do you guys want to split it apart, or do you want to just leave it as one big group? We're okay with leaving it? Okay. So what should we do to the first piece? Add 1. Divide by 3. So we have 6 divided by 3. 2. So 2 theta to the third. Okay. Minus. What do I do with the 7? We leave it, just hangs on. And then what did we take the derivative of to get to secant squared? Tan. And so it's tan. Tan theta plus c. Somebody saved us from killing an animal. Good. If anybody else ever watches my YouTube channel, they're like, why are so many animals dying? Okay. And that is all I wanted to show you. So now we're doing exactly what we learned in the video. We're doing exactly what we learned about this notation, and now we're just going to practice it, and that's it. Alrighty? So nose goes, grab a book.